There used to be a full screen option. I swear. I guess it's so small though. I don't know what happened to it. Okay. So, quiz today will be very similar to this idea, instantaneous rate of change in a few different ways. So the first one, we're given 5x squared minus 2, estimate the instantaneous rate of change at x equals 2 if h equals 0.001 in either direction, which means you get to choose, but you just have to calculate one of them. I'm going to do both of them just in case. But so remember, this kind of h notation is essentially telling us how close they want us to take the other point. So we're essentially going to use 2 and 2.001. So we would need to plug both of those into the function, because remember, we find the estimate for the instantaneous rate of change using an average rate of change. I don't know what these are off the top of my head. I should have had to calculate it out already. 18 point. And remember, the other thing with these is you want to kind of take as many decimal points as you can. So in this case, we end up with 20.005. And if you wanted to go the other way, if you will, and let me try to zoom in on the calculation, I guess, a little bit, just to make it a little bigger. If we wanted to go the other way, we could use 2 and 1.999. And just like with normal slopes, because these are slopes, it doesn't matter which way you put the terms as long as you're consistent. So you could put the f of 1.999 first as long as the 1.999 was in the denominator first. Anyway, this one would give you, nope. This one would give you 19.995. Again, since I didn't specify a direction, it said either direction. Either one of these would be perfectly fine. You just have to find one of them, not both, but whichever one makes you happier. Questions, concerns on how I found that? Okie dokie. Then for part B, you're told we want to let h now be 0.01, and we specifically want to go to the left. When I talk about right and left, think about like a number line, and the number I care about is 2. If I'm talking about the left, then I have to take a number that's just to the left of 2, so we would end up with 1.99 in this case. And if I wanted to go to the right, it'd be 2.01. So we're using f of 2 minus f of 1.99, 2 minus 1.99. This is also going to be very close to 20. $19.95. So it makes sense that all of these are, very, very close to each other because they're all using 2 and they're all using things relatively close to 2. Questions, concerns on how I found that one? Cool. So, and then yep.
Okay, so for B, where it says 17.8005, but I think I remember in the video you said at least 4.
So at least 4.
Okay.
If I take more, it's fine, but you should probably take at least 4 decimal places. There are some cases where it might not have 4 decimal places. Like if it just came out to like 17.5, then just take 17.5. But, oh, you mean for like, sorry, no, keep going.
For B.
Mm-hmm. For this piece, all right?
Yeah.
So I have 4 decimal places.
Okay. Oh no, I was asking because I think I remember in the video you said okay, yeah, at least take at least 4 decimal places. But I was just sure like it does fully answer because like after the fight.
So I think that's actually all of the decimal places I get from that number. When I plug in 1.99, this is exactly what I get.
Oh, okay.
Even if it wasn't, even if it continued on, if I stopped here, that'd be fine.
Okay, that works.
But yeah, in that case, it actually cut off after 4 decimal places anyway. All right, cool. How do we get, oh yeah, doesn't matter what side the f of 2 is on when you set up the equation. Brianna, no, so say, look at this one again. If you were to calculate, maybe I'll do another color so it's, well, maybe blue. If I did f of 1.999 minus f of 2 over 1.999 minus 2. So the only thing is that you have to keep the kind of 1.999s together. Oh, it's lagging. Oh, the lag. There we go. So as long as you kind of keep the same number together, if you will, it doesn't matter which one you put first. You'll get the exact same answer once you finish it. How did we get the 18? Yeah, so Sydney, thank you for that. You were plugging in 2 into the equation 5x squared minus 2. Ah, yes, that will make a difference. All right. Any more questions? All right. Then for the second one, this is kind of the second idea we had for finding instantaneous rate of change, which remember is equivalent to the derivative. So asking for f prime of 25 would be the same thing as the instantaneous rate of change at 25. But now because I have a table and I don't have something obnoxiously close to 25, I essentially need to do, this is where we kind of have to do 2 things. We have to take the average rate of change kind of on both sides, and then we're going to average the 2 together. So first thing I need is the average rate of change. So I'll try to scroll up, you little dork. There we go. Average rate of change between 25 and 30. We've got 14 minus 9, or 9 minus 14, as long as you're consistent. 25 minus 20. So 5 over 5 is 1. No, wait. Now, okay. I did it backwards of the way I thought I was going to do it. Now I need to go from 20 to 25. Oh, no, wait. So I messed it up. This one is from 20 to 25. And now we'll do 25 to 30. Sorry about that. I'm going too fast for my own brain. 25 to 30, so we'd have 21 minus 14 over 30 minus 25. And I should have changed this from the other day. You can tell how bad I am at arithmetic because I thought this was going to come out to something super nice, and it doesn't. It comes out to 7.5, 7 over 5. What is wrong with me? Which is 1.4, I believe? Yes. And then once I have those 2 average rates of change, I want to average them together. It's unfortunate that we have average rates of change that we're averaging, but, you know. So we add the 2 up, divide by 2. 2.4 divided by 2 is 1.2. So your estimate for the derivative there, derivative value of 25 would be 1.2. Questions, concerns? Cool. 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 At the very end, Ashlyn, it's not going to be there right now, but at the very end of class, it's going to pop up under the assignment tab, and you'll just take it on there. It'll pop up all the questions. You'll type things in boxes and call it a day. Okay. I'm going to talk about the exam for like the quickest second of my life. Well, don't look at that. Nope. Let's go and unshare that. And let me pull it up over here for a second. Sorry about that. I like how I did this to my screen like that was going to change anything for... So if you're in person, you obviously got your exam back to your face. That's, I don't know what's wrong with me today. I'm sorry. But the scores are now in Blackboard as well. Literally just a few minutes ago. So if you didn't see it already, they're up now. I just want to talk about something really quick, just to give you an idea of some things that, it's so tiny. Let me get rid of the chat really quick. That'll help a little bit. Just a couple of things. So if you have it in front of your face, you'll see, especially on the multiple choice, if you didn't get a 4, that means you got it wrong. I don't like, my heart can't handle giving you nothing for it. So if you get it completely wrong, you get half a point. Hooray. And if you showed some kind of work, or I kind of followed where you were going and you kind of, or like there was the slope one where maybe if you just had it flip-flopped, I'll give you a couple points out of the 4 because you were close. But if you didn't get a 4, then you didn't get it right. On the find the error ones, there were a couple that actually I didn't mean to be errors. This is why I shouldn't write an exam at 10 p.m. at night. For instance, this one, there's actually a small error where the sign turned into a negative instead of being a positive. If you pointed that out, you got full points. If you didn't point that out and you said they were correct, you also got full points. Because what I was trying to do is I was trying to make it completely correct, but somehow I forgot to make it positive. On these questions, if you have some in the future, I'm never trying to trick you with really small errors, and I would consider that a really small error, which is why I could have just said, oh, well, I messed up. If they didn't pick it out, then they didn't get it right. But I was like, no, that's too small of an error. I don't like that. So I kind of accepted both answers, even though that technically should be a plus sign instead of a minus sign. I don't do, forgot a negative kind of errors, which also happened on the next one. Don't write an exam at 10 p.m. This should have been negative 1/3. If you figured that out, you got an extra point. If you didn't figure it out, I didn't care, because the two main errors here was that their setup was backwards. It should be Q equals F of P. And they plugged in the slope into the completely wrong spot when they were solving that. So those were the two errors I was trying to go for. And if you picked out the error that I also forgot a negative, because 46 minus 70 is negative 24, you got an extra point. Everything else was okay, I think. Yeah. So yeah, there's that. Scores are on Blackboard. Answers will go up. I'm going to try to do that before I go home today. So that's the thing. All right. So now I actually have to go share this. So 2.4, we barely started. I kind of ran through it at the very end for the last couple seconds. I tried to talk about it a little bit. So we're going to finish that today. Hopefully start 2.3, hopefully. And then we'll take our quiz. So I'm going to kind of walk through this somewhat quickly because, again, I kind of already presented the idea behind it on Tuesday. But essentially what we're doing here is we have this function. And Desmos is being our best friend, and it's graphing all of the tangent lines for us. So it's graphing these tangent lines, and what we want to do is we want to estimate the slope of the function at those points. So we're going to use the slope of the tangent line. So I think I talked about the first one the other day. I really want to get up and point at the screen, but then people won't be able to hear me on Teams. So if I want to find the slope of this line, you know what? If I want to find the slope of this line, look at this, this is great. Then if I start here, if I move over 1, I can kind of count up how many I go up before I hit the line again, and that'll give me the slope. So I go up 1, 2, 3, 4, 5, about 5.5. So we're going to say that the slope, oh, this is going to be fun, that the slope at x equals 1, sorry, x equals -2, we're going to say that that's about 5.5. I'm going to keep track of them right here because I don't have the notes pulled up. Once I jump back to the notes page, we'll write them down there as well. And then if I move over to -1, I've got a new tangent line. So if I find the slope of that guy, if I move over 1, I kind of have to hop up 1 and approximately 2. Let's just take it to the, the nearest half for our own sanity. So we'll say the slope of this line is approximately 2. So at x equals -1, I forget that it's on this screen. At x equals -1, the slope is approximately 2. And if I keep doing that, so I'm going to start doing them slightly quicker. Stop me if you want to ask a question. So the slope of this line, if I move over 1, I go down. Now it's not quite down 1, but again, for our sanity, let's just go ahead and say that's -1. Let's just round up to the kind of the nearest thing. So we'll say at x equals 0, the slope of that would be -1, and negative because we had to go down, right? Well, what about at x equals 1? If I find the slope of that line, I go over 1, down 1, 2. Okay, hold on. 1, 2. What did I put on my notes? 2. Put 2. So that's approximately over 1, down 2, because we kind of start a quarter of the way up, and we end a quarter of the way up. So that'll be approximately -2. So at x equals 1, the slope of the tangent line, which would give the slope of the function at that point, would be equivalent to approximately -2. Is that making sense? Okay, I know I'm kind of breezing through them, but I think after doing 2 or 3 of them, you kind of pick up what I'm saying. But if you don't, just let me know. Oh, well, now I've run out of. What about at 2? Go over 1, go down 1, down 2. Let's say about 2.5. So at x equals 2, we'll say that the slope is approximately -2.5. This is also lagging for all of its years. I'm going to kind of just say these last 3, and then we'll pop over to the other side and we'll write them down. So the slope at 3, we go over 1, down 1.5. So we'll say the slope at 3 is -1/2. We'll go over to 4. 4. Say we go over 1, up approximately 1. This mouse is not following me very well. Go over 1, about up 1. So we'll say the slope at 4 is 1. And then one last one at 5. Let's go backwards because that kind of runs into some things there. So if we go back 1, we go down 1, 2, 3, 4. But since it's left and down, the down cancels out with the left and it'll be +4. Also because the line's going upward. So we'll say the slope at 5 is +4. Now again, usually I do this as a kind of activity for you guys to do. So it didn't transfer over as well as I would have hoped. But here is the point. So we were looking at this graph and we were given a bunch of the tangent lines that, I'll probably draw on here before I post it on Blackboard. Go away. There we go. So, we had a bunch of the tangent lines. We found all their slopes. So let me write down all of those. Oh, I already did. I forgot what I did the other day. So I wrote them down the other day, but that's how we would have found them because I don't think I went through all of them in generality. And then what we're going to do from there, which we did yesterday, I'm just remembering how far I got rambling the other day, but I did it really quick, so I wanted to go through it one more time. Then we took those slopes and we plotted them. And we said that, hey, that looks like a parabola, even though it's drawn very poorly on my end, but it looks like a parabola. And a parabola is a function, right? It's just, it is. So essentially what we found is we found a function of slopes, if you will. So what that's going to give us, I don't think I defined this, I did not. So a definition that I didn't write, out there in text. So for a function, we define the derivative function and derivative function is kind of what we're defining here. So we define that kind of new function in the following way. The y values are essentially going to be made up of these derivative values, of these slopes of these tangent lines. So it's going to be the instantaneous rate of change of f at x. So essentially what I'm saying is we can define a function kind of in this way I just did. If we take a bunch of the slopes and we just make a function out of those slopes, that will be a derivative function. So not only is the derivative a value, it can also be written as a function. We can also have derivative functions, not just derivative values. And the big thing that is going to come back to bite us in the butt so many times is what I'm about to write down right here. You'll want to have it in your brain, eat it, sleep it, dream it. I don't know. Okay. Anyway, the point is we kind of have this relationship between the two. So if the derivative value is positive or greater than 0 on an interval, then the original function is increasing on that interval. If the derivative value is negative, there we go, that's a little better. The derivative value is negative, then the original function is decreasing on that interval. And if the derivative value is equal to 0, then the original function is constant on that interval. Eat it, dream it, sleep it. Stick it on your forehead. So let people get that down. So kind of the point of 2-2, what we're going to do now, kind of the point of 2-2, is we're going to be able to be given a graph of an original function. And given some choices, we're not going to have to really draw them from scratch. I don't believe. There might be one on Wiley, but I think that's a lie. But we won't really have to draw them from scratch. But if I give you some choices, can you pick out the one that will give you the derivative graph? And we're going to be able to do that by using this relationship between the two. So let me try to kind of point this out using the two that we currently have, because we have that kind of curvy function that we were looking at on Desmos, and we have our parabola. So what I want to do now, I don't think I have it set up for it yet, so give me one hot second to get this out again. And now what I want to do is I want to unshare that, and I want to reshare just my screen, and I'm going to go blank. And this. Zoom. And so let me erase that. And then here, I want this, and I want you to go away. Okay, so let's kind of look between these two functions and kind of see what I'm trying to talk about here. So notice on the derivative graph, so the one on the right, the parabola, it crosses the x-axis, right here and right here. So let me go over to my original function and try to figure out where those x values kind of land on the function. And now, since we were estimating the derivative values a little bit, it's not going to be 100% perfect, but just trust and believe that I put these things where they should be. So it kind of crosses the graph between 0 and 1. So it kind of crosses, right here. And it also crosses kind of between 3 and 4. So, probably about right here. So what do you notice about the original function in those two spots? Yeah, you use fancy language that some people don't know, but yeah, totally. So those are the maxes and the mins of that function, right? That's not a coincidence. That's what's supposed to happen, essentially. So if we also look in here, so in this kind of leftmost section of the original function, I'm increasing, right? And then kind of in that middle section between the two giant doodles that I've made, then we're decreasing and then we're increasing again. I kind of cut the function off a little bit, but it increases for the rest of it. If I come back to my original function and split it up in those sections as well, now this one, I think for some reason it's weirder for people to think about, but notice that this leftmost piece is purely above the x-axis. None of it is below the x-axis, which would mean we would consider this piece to be positive. And then this middle piece is completely below the x-axis. We would consider that piece to be negative. And then the last piece is purely above the x-axis, so we would consider this to be positive. And that's what I mean by that relationship that we just wrote down. When the original function is increasing, the derivative is positive. And when it's decreasing, it's negative, and so on and so forth. So this is kind of the idea that we're going to use to be able to kind of pull out the correct derivative graph, is we're going to kind of look and see where the one function is increasing and decreasing, and whether that means the other should be positive or negative and what pieces. So I'll leave that up for like 5 more seconds. And then I got to unshare and reshare something else again. This section, the way I usually run this section does not go over well with online learning. But anyway, so let me unshare that really quick and reshare just this one. Why is it so small? Oh, there we go. Hooray. So, well, now I'm doodling all over this thing. So some notes. So determining the graph, the derivative graph, given an original function. How the frick are we going to do that? We have a couple things that'll help us out. The first thing you're going to want to do is you're going to want to locate the maximums and the minimums of the function. At these points, the derivative will be 0. That's kind of the first thing I pointed out between those two. Wherever it crossed the x-axis, the derivative, the original function had a max or a min. Now, if the derivative is 0 there, then you kind of have 2 options, but also not really 2 options. I'll say more in a second. So it should either touch or possibly cross the x-axis. Now, for a max or a min of the original function, this will mean that the derivative crosses the x-axis. The reason I add in touches there is because it could also touch the x-axis, but kind of just, give it a little whoop. That didn't even touch, but pretend that touched the x-axis, but not actually cross the x-axis. That's totally possible. But for what we're finding in terms of maxes and mins, it actually will end up always crossing. But just because, so the reason I make that distinction is the first thing we always do with these things is we find the maxes and mins and we say, okay, the graph of the derivative should only cross that many times. But it could touch in other spots as well. Those ones are harder to find, but essentially this second piece will always take care of that. But just know that even if it doesn't cross the x-axis, if it touches the x-axis, that's okay. But the ones we'll be looking for are specifically crossing. Hopefully that'll make more sense when we do an example in a second. Like 80% of the time, that's all you need. You'll usually just be able to find the answer from that just one option. But say you needed some more information. What you're going to do then is you're going to determine where the function is increasing and where it is decreasing. Kind of that second piece that I was just talking about, where I split up the original function into its pieces and then the derivative graph was positive, negative, respectively. So the derivative will be positive and negative in these intervals. Negative, my pen freaked out. In these intervals respectively. So when the original is increasing, the derivative is positive, decreasing, derivative is negative. Those two will solve it 99% of the time. And in terms of the ones we will look at, 100% of the time. But in general, sometimes you might need a tiny bit more information. If you wanted a tiny bit more information, what you would have to look at, because essentially without any more information, we don't know what it's doing above or below the x-axis. We just know that it's above or below. We don't know exactly what it's doing. If you wanted to try to figure out what it might be doing, what you would have to look at is you'd have to look at the steepness of the tangent line. Look at how steep, I guess, is the correct English for that sentence. Look at how steep the tangent line would be to get an idea of how large the derivative value is. The steeper the tangent line, the larger the y value for the derivative should be. And if it's steep decreasing, then it'll be a very large negative number. So you also kind of need to take into consideration whether it's a positive or negative slope as well. Kind of a side note, if you wanted to try to use this idea of the tangent line, say you're really bad at drawing tangent lines like me. So remember, the definition of tangent line means that it only crosses at one point in kind of that small interval around the point that we care about. But if you're having trouble visualizing the tangent line and you want to try to draw them, pick a point really, really close next to it and just draw the line between those 2 points. That is not an official thing. That's not actually how tangent lines work because it only touches the function once. But it is kind of like a cheat sheet way to just kind of draw it easily. So don't go telling, other professors that I said that tangent lines touch more than once because I'll get fired. I'm kidding. I hope. Anyway, I'm going to stop talking. So those ideas are what we're going to use to try to figure out these graphs. We'll come back to the kind of other direction in a second. So let's see some examples. So I know, especially on this little tiny screen, they got really blurry. I'm really sorry. Honestly, even though they're kind of blurry, we have enough to know which one it's going to be. So let's see how this would work. So the first thing was that we wanted to find the maxes and the mins of the function. So we have a min here and a max here. Whoa. Oh, stop it. Stop. I really don't know what I do that makes it zoom in. And I swear, I'm not this technologically dumb. Anyway, I'm personally going to kind of split this up at those two sections as well. So we have that this is about x equals -1 and about x equals 2. You don't have to be perfect, just get, the general idea of where it happens. So since we have a max and a min in those two spots, that means that the derivative is guaranteed to cross the x-axis at those 2 points and nowhere else. Nowhere else would it cross the x-axis. It might touch the x-axis in some more places, but it cannot cross the x-axis in any more places than those two right there. X equals -1 and x equals 2. So the first thing you can kind of do is look at your choices and look to see how many times it crosses the x-axis and where it crosses the x-axis. Option A crosses the x-axis 3 times. That means it's out. Crosses 1 too many times. B and C are essentially the same graph but flipped over. And they do cross the x-axis essentially in the correct spots at around -1 and around 2. So we essentially come down to options B and C, and now we need to figure out which one of those two actually works. And this is where you go to that idea of the increasing-decreasing relationship. So if I go back to my original function is increasing. No. My original function is decreasing in that leftmost piece. and then this middle piece is increasing and then decreasing. So if I get another color up in here, and I wanted to talk about the derivative. Well, if the original function is decreasing, that means my derivative is going to be negative in this piece, and then positive in this piece because the original is increasing, and then negative in this piece. You don't have to be writing all these down when you're doing them formally. When you get really good at them, you can kind of just look. But if you need to write them down, go right ahead. So I'm looking for something that is below the x-axis, then crosses to be above the x-axis, then crosses to be below the x-axis, which is the only option C, because option B is essentially backwards. It's above, above, and we need below, above, below. Now again, I don't give a crap what it's doing above or below the x-axis, as long as it is above or below the x-axis. So the answer there would be C, because B is kind of the opposite positive, negative pieces that we would have needed. Does that make sense? Okay. Questions, concerns before going on to the next one? Okay. Same idea, different function. First thing, find the maxes and mins. We got 3 of them. One of them's there, one of them's there. I drew that line a little wonky. I drew that line even wonkier than that one. So we've got it approximately -3.5, approximately 0, and approximately 3.5. It will cross at those places and those places only. So let's start looking at our function options. We have that this crosses once, twice. It kind of touches over here, but it doesn't have a chance to cross again. So it doesn't cross 3 times. So that option's out. This one crosses once, twice. And if I want to be super picky, it technically does cross right here. There's this little tiny sliver above. But it doesn't cross at 0. Like maybe these ones over here are a little ambiguous of whether or not they're crossing in the right spot or not. But it's definitely not crossing at 0. And I needed it to cross at 0. So this one's out. Though I'm going to talk about it a little more too, so I'm going to not cross it out really quick. But that is a way that you could say that that one's not an option. It crosses 3 times if you really want to include this last bit, but it doesn't cross in the right spots. I'm going to keep it just in case I want to talk about something else. And then this last one does cross 3 times, and they do seem to be kind of in the right spots. So again, we're kind of pretty sure it's going to be C, but let me just babble about it a little longer. So if you weren't sure, say you were keeping part B in the running just for giggles, well, then the next thing you would be looking at is the increasing, decreasing piece. So if this first piece is decreasing, I know my derivative is going to be negative. It needs to be below the x-axis. In both B and C, we have that happening. They start out being below the x-axis. Then in this kind of second piece, we need to be positive because my original function is increasing. Well, both of those graphs switch to being positive, so we're okay there as well. Then it has to switch back to being negative, with both of those graphs do. And then switch back to being positive. Now, again, if you're being super picky and you count that little sliver that y'all can't even see because it's too blurry, if you want to count that little tiny sliver as above, technically, but notice how we have this large interval of the back that should be increasing and should therefore be positive on the derivative. That little piece is so tiny that it doesn't count. So like even that kind of crosses it out as well. Does that make any sense? I always feel like this topic is like super weird and I have to babble for 5 years and then I think everyone's just like, shut up. Yeah, it's okay. Okay. Maybe I'm just making a fool of myself. I do that a lot. So anyway, questions, concerns before I go into the next one? So we'll do one more in this direction, then we'll do one in the opposite direction. So I'll have you guys look at this for maybe a minute. Try to figure out which one it might be, and then I'll talk about it. So I'll give you a minute. So with this one, again, it's kind of like the first step already gets you the answer. Because it has two maxes and mins, well, one of each, but two maxes and mins. So the derivative function can cross the x-axis no more than 2 times. Option A and option B cross more than 2 times. I did not mean to have all of these be C, but oh well. So the option here was C, and to triple check, our derivative should be negative, then positive, then negative. So our derivative value, which this is, it's below the x-axis, then above the x-axis, then below the x-axis. So that's another way you could kind of get some of those choices out of the way. Option A kind of doesn't follow that pattern. It needed to be negative first, but it's positive first. So that's another reason why A is definitely not the answer. And then you can also notice that B starts out negative, so it goes negative, positive, negative, but then it switches back to positive, but we didn't have a switch again. So that's, you know, if step 1 of the maxes and mins don't get it for you, you can always try to talk yourself through with the increasing, decreasing piece. Questions, concerns? Yeah. You're talking about here? So when we're looking at the original function, so teams, he's wondering if we have to care about 0 on the original function. So when we're looking at the original function, the only thing we care about is a maximum or a minimum. Is that a maximum or a minimum? No, so we don't care about it. We don't care where the original function crosses. What we're being told is when it has a max or a min, that's where the derivative should cross. So it's kind of, so yeah, it doesn't matter that it crossed the x-axis there on the original function. That doesn't tell us anything about the derivative, so we don't care about it. All right, let's go the opposite way then. So let's write down the process for going the opposite way. This is taking way longer than I expected, but it's okay, I guess. So going the opposite way, say we're given the derivative graph and we want to try to figure out which one was the original function. It's kind of the same idea, but just kind of backwards. So the first thing you're going to do is you're going to locate the zeros of the function. What I mean by that is where it touches or possibly crosses the, I lost it, the x-axis. So instead of looking at maxes and mins, you're now looking at where it crosses or touches the x-axis. Ooh, here I am making that tiny little mistake again. Ooh, ooh, ooh. Let me finish writing this and then I'll babble for a second. At these points, the original function will have a maximum or a minimum. I can't believe I didn't catch this when I wrote these. I'm going to erase, not erase, but I'm going to cross out where it touches the x-axis. Those are kind of points of interest, but they will not result in a max or a min necessarily, or at all. They won't. So since they don't result in a max or min, I actually don't want to consider them. Sorry, I don't know why I put that in there. So look for where it crosses the x-axis. You're going to determine where the derivative is positive and where it is negative. So where it's above the x-axis and where it's below the x-axis. It should pretty much be split up with those points you just found where it crossed the x-axis. The original function is going to be increasing and decreasing respectively. Essentially the opposite of what we were doing before. And once again, kind of those first two things are enough to tell you pretty much 100% of the time for us, but otherwise 99% of the time. Without any more information, we can't really know what it's doing, kind of above or below the x-axis, or anywhere, what it's doing anywhere. But if you wanted to try to look at the y value of the derivative, that would kind of tell you how steep the function is, so you could kind of figure out if it's like going upwards really fast or upwards really slow, or kind of turning back around. But again, we don't really care what it's doing. The other two pieces are kind of enough to figure out which one it should be, because we're just picking them out of choices. If we were trying to draw these from scratch, that would be a different ball game. So I'll give like 5 more seconds to get that down. And we'll do one example of that. Then we have to take our quiz. That's unfortunate. So, a couple more seconds. So the first thing we want to look at is the zeros of the function. So here's so the big one here is now the derivative graph. So first thing I want to do is figure out where it crosses the x-axis. Crosses, it technically crosses, but we probably won't really need to care because it's so close to the end. So we know that the original function, now I think going backwards, especially going the other way for 3 examples, now having to switch your brain over, this one usually trips people up a lot. So we've found where it crosses the x-axis. I'm going to leave that last one out because, again, it's so close to the end of the function that it's not really going to help us out a lot. We're going to have a min or a max. Now, if you know a bit more about calculus, you can figure out which one it's going to be, but we don't really need to care which one yet. We'll figure out how to figure it out later. So we need the function to have a maximum or a minimum, we don't care which, at both of those points. So at about -3 and about 2. Well, at A, it doesn't quite have a max there, but just in case, maybe I'll keep it in the running if I'm, because here it looks close enough. So I'll keep that in the running just for giggles, even though this is so far off that you can pretty much count it out. But let's just keep it in for giggles. And then if I look at the second one at -3 and +2, well, that one looks really good. So we'll definitely keep that one in. And then at -3 and +2, well, that last one doesn't have a max or a min near those spots at all. So let's definitely cross out C. Now again, technically it's going to be B. And you can, if you said that right off the bat, you'd be fine. But let's say for giggles you left A in. So what we'd need to look at then is, so the derivative graph, what I meant by the original is the big graph. The big graph, which is the derivative graph, starts out negative and then positive and then negative. So what does that mean about the original function? We're going the opposite way now. So the original function would have to be decreasing and then increasing and then decreasing. So which one of those 2 options we have left starts decreasing and then changes to increasing and then goes back to decreasing? The only option is B, because A starts out increasing, so that wasn't the correct option. Make sense? I had such high hopes for this week. I was like, we're going to get through 2-3. Everything that's on their homework is going to be covered by Thursday. I finally rocked it, and now I didn't. Which probably means I'm going to give you a 2-day extension on your homework to Thursday, because I really don't want the entire 2-3 to be on there. And I'm sorry that this keeps happening, that things keep getting so messed up. I really thought we were going to get through 2-3 by today. We were actually supposed to cover 2-4 today, so I'm really behind. So that's the thing. But I mean, you have 2-1, 2-2, so I mean, you can start it. You can get a decent amount of it done. But obviously, we haven't talked about 2-3 yet, so can't do that. So we'll talk about 2-3 on Tuesday.